So very quick introduction about myself. My name is Sharat Singh. I'm CEO and Chief Architect at Quadrical AI. We at Quadrical AI are a B2B SaaS AI startup focusing on building data AI platform, specifically for high performance prediction and anomaly use cases. Our core products using our data AI platform are in the renewable energy and retail e-commerce space. So with that, let me just start off with our talk. So as I noted in some of my, can you guys see this? All right, looks like you are able to. Okay, so as I noted as part of the chat, it is somewhat medium or advanced topic. The basic topic that I'm trying to cover is, as you build and deploy various AI ML models in production, there are quite a few trade-offs we make in terms of the choices of the model, et cetera, et cetera. And I'll cover that in a little bit detail later on. So part of this is, how do you, beyond the initial set of deploying these models, how do you take care of the life cycle and what are the quality considerations? So one of the core things that as we built our products out, that we operationally, as part of our applied research things that we implemented, was an aspect of quality aware models. So we'll cover that in a lot more detail. So very quickly about our background so that you know the context and the folks who are kind of behind some of this thinking. Quadrical AI, as I said, is a SaaS AI startup. As part of our data AI platform, our core innovation and expertise is in the area of predictions and anomaly. So, and many different customers' data set all at the same time. So the aspect of how we are able to tease out the variety of different cardinalities and shapes and distribution of different types of customers to a common set of problems is massively important to us. So jumping into this right away, what do we mean by data feature drift? As I said in the introduction of the talk, and as we noted earlier on, there is a standard data drift that happens. So essentially, you create a model, you do all sorts of things in terms of what your train set is, what your eval set is, what the test set is. And as you deploy the model, you somewhat think that the test data or items that you're going to be scoring on a daily and regular basis are somehow going to be similar to the items that you created the core data on. And then anytime there is a shift in terms of the distribution of the data or the signature of the data between train and test, you will see model degradation because your model doesn't quite understand how to predict the outcome of the data that it has never seen before. So obviously the drift can translate into the most common drift that everybody is fairly comfortable, and we've seen it around happening enough number of times, where the seasonal changes in the environment can lead to, for example, different daytime hours, different temperature, different humidity patterns. And for us, as part of the yield prediction for the solar plants, that can be that causes enough disturbances where if we didn't model it properly, our yield prediction would be erroneous. But again, this is a fairly solved problem when it comes to ARIMA variations, how longitudinal data can be used in training, how we can use variety of signals about the seasonal information into embeddings and other float variables. So this is not what this talk is going to be about. What we're going to focus mostly is around things which are related to gradual drifts. Environment changes, you will see more and more data that you may not have seen before, at least for the more complicated problems. Everything in life is a little bit more complicated than what we learn in the labs. So as your environment changes, your model will at every point, at some point or the other, will have to look at data that it has not seen before. Then the notion or the idea is, how do you go about fixing that? And again, some of the examples for that happening is, for example, in a marketplace where we were trying to predict airline ticket prices, we would see, because of different disruptions in a dynamic industry, new players would come, existing players would leave. The supply and the demand would shift over time because of unnatural reasons, as in disturbances to the economies, as in inter-border issues, etc., etc. So those are things that you cannot really model. Similarly, there are other types of degradations or other types of drifts that are expected. For example, in a 20-year life cycle, a solar plant would expect to see PV solar cell efficiency degrade, but that's expected, and your model should be able to tolerate that drift. Similarly, there would be other types of degradation or drifts where the solar plant output could be degrading because of soilages. So again, there are going to be drifts which are going to be acceptable. There are going to be drifts which are not going to be acceptable. So the notion is you have to be able to deal with that drift. And typically, right, I mean, the easiest thing to do as such drifts happen is you retrain your model. While we can do some of this retraining, as I said, there are nuances to the drift that we want to bake in and the nuances of this drift that we don't want to tolerate. So if I retrain and reset the clock for my predictions to deal with the notion of soilage degradation being acceptable, then my overall platform will not be able to identify soilages and give prediction indications to my customer saying, hey, there needs to be a maintenance cycle to clean this up. From time to time, I'll kind of pause and make sure. I should have set up a dual screen, but as I slide back and forth, I will want to make sure if there's any questions or discrepancies in the chat window, I can respond to that. Okay. So as I said, so the core portion of the talk is going to focus on saying, as you deploy models, what things you should be thinking around in terms of generalization techniques, so that you have to do less and less of hand-holding in production, including retraining. And by the way, this is not an either-or choice. You can, depending on your business environment, you can as effectively say, hey, look, I'm happy retraining my models every day. So if that is the case, you do not gain anything from this chat. Of course, similar to the gradual shift, there can also be sudden shifts. Sudden shifts where there are systemic events which are actually changing the behavior and the environment as a whole, which means any parts of the trainings that you may have done actually become useless or provide weak signals, right? So whether it is in the solar environment, whether it is extreme weather events, or in the retail or e-commerce environment, there could be seismic decisions as part of the governments as to how that affects the economy, or what we're all going through right now in terms of the consumer behavior changing because of the global COVID situation. Again, while you can solve some of these problems by retraining and transfer learning, we have been effectively able to solve them also with better generalized models. And just to complete the picture, right, I mean, there's also another field of drift, which could be model-driven actions inducing data drift or feature drift. And this is, again, one of those examples where if you're solving a problem related to intrusion detection and you're successful, then obviously the intruder is going to innovate in useful ways, and your model would also have to kind of keep on working on finding those intrusions. So it's one of those things, if you're successful, that's going to breed more challenges and failures for you. But again, there are other approaches in terms of reinforcement learning and other use cases to go solve it. This chat is not, or this talk is definitely not about that either. So again, generalization, let me just quickly first do this. Generalization as an approach is massively important in terms of building any scalable, useful model. We assume that And a lot of this chat or the talk is going to be based on our hypothesis that we want to build multi-models again for sophisticated problems. Our architecture should be multi-model architecture and not a monolithic. And as I said, either of the architectures that you choose, you will always have to exercise the due caution related to generalization. And again, it's whichever architecture you use, we expect that you will use all the appropriate techniques of data augmentation, dropout, regularization, making the right choices of train, eval, test, filtering out outliers and anomalies, and so on and so forth. What we're saying is for more sophisticated use cases, even when you do those things, there's no guarantee whether your test data is going to be reflective of the trained data that you've used in the future. And again, you still have the choices of retraining, but essentially where we're leading to is we want to create models which are more resilient in production and do not require significant amount of training. Again, just to put those two architectures in perspective, a monolithic model can also have multi-stage boosting and other approaches. But again, those could all be out of the box in one single model. When you do that, it's actually very, very compelling choice to make, where it is easier to build. You can optimize it through brute force. Wherever there's hyperparameter tuning, there are all sorts of packages out there which would throw compute resources and do a variety of auto ML techniques to give you the right hyperparameters. And once you build that particular thing out, right, the pipelines are fairly simple as long as you take care of this monolith in a reasonable manner. The obvious challenge with that is it's very compute intensive, or can be. And any retraining requirement also comes at a reasonable cost. And then again, any retraining, this element is also similar as we compare. The assumption is you're sanguine enough to understand how to handle the recency when you do the training, how to handle incremental training, and you can optimize things in transfer learning. So again, the notion of the thought is these techniques could be applied to either the monolithic or the multi-model approach that we're suggesting. So again, we prefer in addition to standard generalization, we are able to achieve significant more generalization through the multi-model architecture. Before we even go down and talk about as to what that is, let's talk about the pros and cons there. We've been able to gain significantly stronger performance out of those, again, because our ability to fine tune and handle the fidelity of the systems a little bit better. They're easier, cheaper, operationally much more robust with fewer retraining. The big downside is it requires a lot more thought and upfront engineering to manage some of these pipes. So again, not everything is for everybody, but essentially if you are in a sophisticated environment where the ROI justifies the upside, then this particular approach makes sense for you. By the way, for us, it makes absolute sense because as a platform that is being used by a variety of companies, we are able to put in that investment in those pipes and the engineering to tap onto the additional capabilities and performance that we're looking for. So I want to pause a little bit because I want to see if there are any kind of questions or any things that people may have before I can jump through the rest of the slide. Okay. So Diana, you mentioned that I need to double click the slides. I was already previously doing it in a slide share mode. I was expecting that the slides should already be in full screen mode. Is that correct? Yes, absolutely. After the deck, we can share the slides. So one question I want to pose is so right now I'm looking at a browser view where obviously you're seeing a split window, but when I do the slideshow, are you able to see the slides in enough granularity and details to follow? Okay, thanks, Arnaud. So I'll go back to the deck. So as I said, the rest of so we're making a few assumptions. We are making a few assumptions around saying, hey, your ROI justifies the need for complexity, which is going to give you much higher accuracy. The models are going to be more resilient, and we're assuming all the standard generalization approaches you're already familiar with. And now the rest of the deck is going to say that if we're willing to make those investments into a multi-model architecture, what else can we do? So broadly, we think that there are three different approaches. One is obviously train your model better. Let me put the three out there and then I'll cover them together. The aspect of, so once you get committed to the multi-model architecture and you have the ability to do that, the notion or the understanding of the multi-model architectures are fairly standard in terms of creating subsidiary, looking for primary patterns, subsidiary patterns, and have different models to focus and the model architectures to focus on those patterns. And then we'll go a little bit further beyond that. Similarly, the notion is no matter what patterns you are collecting, if you create an additional model to understand the overall accuracy of your model, so that as the data shifts and the features drift, you're able to self-correct or tell yourself as to how those shifts are happening and what kinds of errors, are you able to predict your own error rates? And then in a multi-model approach, we can always create a model which does that introspection quality of your model. And lastly, as you take a monolithic apart and break it into small pieces and do things in a more focused manner, you obviously need to have a solid ensembling approach to do this. And the talk is not going to cover the ensembling because we believe there's enough data out there, some anecdotal, but the field is broadly stable in terms of how to handle noise, bias, overfitting, choices of train, eval, test, the k-fold, interaction constraints, and other techniques. So let's just jump into the core of the talk. So when we talk about train better models, so the first notion that we're going to talk about is, look, how do you take a monolithic and create multiple models? Why do you create multiple models? And what's the rationale or the reasoning or the hypothesis for creating those models? So the entire notion is you want to decompose a complex problem with heuristics as to what your primary and subsidiary patterns are. And then you create matching model architectures to focus on those. Sometimes it could be that. Most times it can be that. But in other times, it can also be the generalization of a complicated problem by throwing competing architectures. So when I'm doing embedding, I look at NCF. I also look at whether I'm looking at, so you can have different approaches to process the embedding, right? So whether it is NCF, whether it is deep FM, whether you want to do a one-hot encoding, each one of those architectures are going to extract different types of signals out of this. So the first notion is you go from a monolithic model to go look for subsidiary patterns and create the right model architectures and the diversity in your architecture to capture these things. And I also put in the notion of a data cluster. So then so the minute we do that, this should provide a reasonable boost in your model performance. Once you have done that, then the next thing you're going to focus on is saying, okay, we all know that every model quality improves when you're able to remove some of the anomalies and the noises and the outliers. So this way, your model is not working hard trying to fit things that are not fittable, and in the process reduces the overall quality of the model. So when you have dismembered your monolithic model into clusters or into variety of different models where each model is focused on a different signal, now the question is, what is an outlier and what is a noise? So then the notion of the generalized capability of building a model where you identify outliers and noises based on rule-based. Here the notion is you do it based on the model architecture. So instead of looking at the model inputs and trying to figure out, and again, there are auto encoders and decoders which allow you to identify the outliers or anomalies. We don't, now in this sophisticated approach, we don't take the input data and throw it into autoencoder decoder. We take an intermediate model output layer and we throw that into an encoder decoder, which gives us model specific clusters and outliers and noises. Now, once you have that, that's what we feed into the, then we take that output and then we put that as a model specific input as sample weights to retrain the model. So now suddenly I took a model, I took a monolithic problem, broke it into multiple parts. Each one of the parts, I said, for this part to train better, what is the right data? Once I figured out the right data, I capture that information as my sample weights, and then I feed that into my next model, or the same model again. So this becomes a two-stage model where effectively we're able to extract a very, very strong model with, using this subsidiary pattern. This significantly improves your model resilience. And again, we'll show some results to kind of talk about that in a little bit. Maybe I can just jump to some of those slides and come back. So, and again, needless to say, this still assumes that as you dismembered a monolithic into multiple parts, create multi-stage output of those parts, and now you still have a bunch of different models. You still need an effective ensembling approach to do that. So let me quickly jump a few slides and show some of the results. So typically, again, this is a use case where we created a model scenario where we said we will train the data with everything up until December. So we have 2 years of data leading up to December. So we built a model using that. And then we said, starting Jan, we will not train at all for the next 6 months. So as we create that simulation in a monolithic model, and then we kind of say, hey, so this one is a classification problem, but the notion applies to classification, regression, all different types of problems. Then we said, okay, if I did not train the model, what is my baseline performance as it relates to the coverage? So we consider coverage. So the notion here is to detect the Boolean 1 versus 0. So we are able to find, from a coverage perspective, all the time that event happens, the coverage seems to be pretty, so the red line is the accuracy and the blue line is the coverage. So the coverage is at about, say, maybe 22%, sorry, maybe about 17% or 18%, whatever that is. And then over time, and we did not train the model again, and we just kept on using it to score. So you can see that for obvious reasons, and the model actually did not require any new customer interaction. This was a little bit of a stateless model, but even in a stateless model, from an environment perspective, we see significant degradation from the coverage perspective, but massive degradation from the accuracy perspective. We also picked a data set where there was a key disruptive event happening in the middle of March, which completely tanked the model. And then we put that into perspective, saying if we did if we simply dismembered the monolithic model and we created multiple models of it, what would that look like? So broadly, what we saw was, just a reasonable boost, a little bit to the coverage, fairly significant if you do the denominator as whatever 40. So we went from 40 to 52. So fairly reasonable boost to the accuracy of a fairly complex problem. Then we kind of came back and say, you know what, let's just do this instead of a single stage model, what we just espoused was, you want to do some of the outlier and you want to help each one of these multiple models by cleaning up and refining the data through outlier removal applied as weights. The minute we did that, the model performance beyond the regular boost that we got. So we got a minor boost when we just went to a multi-model. But the minute we went to multi-stage, two-stage multi-model, the boost was much more significant. And also notice as to how the drops were not that significant and the drifts were not that significant. So that's the first part of it. I want to again pause and look through the chat window to see if there are any questions. Okay, so Han is asking, for the multi-stage environment setup, what kind of heuristics are used to determine the models have sufficient coverage of different scenarios, hidden state? And wouldn't it require some other model algorithms that sit on top to control the model switching? So by the way, so Han, this is a domain-specific problem. We are not looking for model switching. We are looking for model ensembling. So within that particular domain, for example, we may decide that this particular domain, we need to figure out the embeddings effectively. So the minute we said we need to do that, then we say, to do the embeddings, I'm going to explore the NCF approach. I'm going to do the deep FM approach. Maybe I want to do deep FM with attention, deep FM without attention. And similarly, the patterns that come out, I want to squint at it from a convolution perspective, or I want to look at it from an LSTM perspective. So it's one single problem, and then you decide that there are n different models that you need. So the idea we are looking at is not to do the model switching, but primarily model ensembling. Hopefully that makes sense. Ryan, you mentioned, do you have a specific example you could walk us through to get a better idea? Short of, so I gave you a bunch of examples, and each one of the examples are similar. So where the examples could be in a marketplace where the airline prices can shift drastically based on how the supply conditions change. They can also shift significantly based on how the economy outlook in terms of the demand changes. And again, I can readjust to that. And again, it's not an either or choice, but then there are other environments which are, so that could be a marketplace example. Similarly, we could have an e-commerce example, which could be reasonably disrupted by, the budget declaration or the Fed announcing, interest rate changes, et cetera, et cetera. I don't know if that's the kind of specific example you were looking for, or if there's anything else I can help elaborate that answer with. Okay, so I'll continue with the talk. So as I kind of illustrated, this is fairly significant, and I can cover as to why it is also fairly expensive, where your domain space and your environment and your ROI needs to be able to justify this level of investment. The second notion is, and again, even the introspection quality is, these are all building blocks. So the introspective quality is again another building block. I can actually apply it to a monolithic model, core model, or this multiple model approaches as well. So irrespective of which approach you used, it still says that, hey, more is better than less. So here the notion is actually much simpler. We're saying, hey, look, we need to have models focus on the patterns that they're interested in. And as we as we identify that subsidiary pattern, we can create the right model with the right target variable. So here what we're saying is you have this black box, and this black box could have monolithic model or multiple models. It generates certain predictions. Now, if I can create a system model or a consumer model for this, which says the predictions that you generated, let me look at those and see how accurate they were. And if I can create a model which can predict the error rates of a core model, that becomes my subsidiary model. And that's what I call introspection quality. So the concept is fairly simple, as long as, again, you have a a different architecture than what your core model's architecture was. This actually produces a lot more significant results around boosting of the model performance as well as resilience. And then again, it assumes that you have a good ensembling approach to do that. So let me quickly jump back to our results. So notice the boost in terms of the performance is even more significant here. And again, I'm not assuming, while I could have applied this introspective quality directly to the monolithic, I am still kind of, in this particular example, applying it to the previous layer. So as you can see, the boost from the two-stage multimodal output is again more significant. The drift is a lot less gradual. The precipitous fall as part of the key event is less impactful. Depending on the scenario and the severity, in some cases, we saw the coverage drop. And again, that's a choice for us. Precision was always more important than coverage. I'm assuming the same holds true for a lot of the participants in this. That's the core part of my talk. So from this point on, I can go down two paths. Depending on the types of questions you have, we can answer those questions. And if you're interested, I can also talk about as to why or how the investment is slightly different. And I can even share details as to how we approach that investment and how your teams can also look at the same thing. So Achint asked that question, can the two-stage approach you mentioned be generalized to end stage, and would the ROI for each stage, even though the ROI is minimal? Yeah, we did try it. So we definitely got greedy saying, hey, is n better than 2? And we were okay with the diminishing returns. But one of the things I kind of skimmed over is, anytime you're doing something this complex, you have to be careful as to how you would reassemble the pieces. So let me just go back to that a little bit. So the fine footprint I put out here was, look, as long as you know, as you're smart enough to understand the ensembling, right? So when you're doing the ensembling, and even when you do the two-stage model, the minute you start doing two-stage model, you will end up creating bias and overfitting. So the only way for the two-stage model to actually work is you need to be very careful where staged. So the whole notion of train, eval, test needs to be taken down to the next level, where the second stage cannot be training on the same data that the first stage trained on. So you'll really need a very, very massive data set. Your engineering starts becoming a lot more complex, where you need every stage needs to look at a different data set so that it is not getting mired with the bias and overfitting. So the answer is yes, end stage model should be better than a two-stage model. And unfortunately, because of the diminishing returns, and B, because of the exponential cost of each stage, we did not see it useful or productive at all. So Blair, I'm new to the introspective quality as well. I have not seen any papers out there which talk about that. So let me go back to. So how does the introspective model know that the prediction is accurate, and does it feed back to the main model? So no, it does not feed back to the main model. It is an independent model which is actually looking at the same prediction and the labels which were also available. So the labels for the prediction were also available to the main model. Given the architecture of the main model, it generated whatever outputs it could. The introspective model is saying, I'm only going to take, so our introspective model ended up actually being a lot simpler. We said, hey, introspective model, all it needs is a simple cat boost, give it all of the features. Even if there are time series elements, you can throw those away. Simply provide to it the input label, the input prediction, which was the output from the previous model, and the target variable is actually the error that we generated from the previous model. So as long as we get the same input as the original input, we get the prediction, and then we train it to get towards a target variable of error. We are able to say that given these conditions, model A for the exact samples that you say would generate this error. So what that ends up translating is your model is creating a surface where it is reducing the errors at an aggregate level. So it does all of the fitting so that it is able to reduce the errors at an aggregate level. This approach is actually telling you what would be the error prediction for each and every individual prediction that it makes. So this is a little bit more complicated, and if need be, we can definitely chat offline. But that's what the thinking there is. Okay. What I can do is we'll keep coming back to questions, and people would have more questions. I want to just also cover the last piece where look, a lot of this is building blocks. It's a lot of choices and decisions each one of us will have to make as to what is the problem we are solving, what is the ROI, et cetera, et cetera. For us, the ROI, given that we're building a SaaS platform, was significant, which justifies the investment. So let's talk about the investment, right? By the way, I'm not trying to sell anybody on this. Our platform, or at least the things that we've built, are primarily for our own consumptions. We provide these capabilities as a SaaS business offering to our customers and not necessarily to the developers. But let me share the notion or the thinking behind what that platform looks like. So as I said, for the most simplistic of problems, the combination of data, some pre-processing, off-the-shelf models, and visualization is sufficient, right? As you get into slightly more difficult problems, you may need more pre-processing, you may need some more cleansing, you may get a little bit more sophisticated on the model architecture, how you handle embeddings and other things. When you get a little bit more sophisticated, you can kind of say, look, all of this needs to be kind of put together. There needs to be an ensembling layer. And then all of that needs to be kind of presented in meaningful ways. And then finally, right, so a more complete system would have more sophisticated pre-processing, the more sophisticated approach of modeling, a lot of feedback loops going into what's working, what's not working. And then as far as we were concerned, we were building a SaaS capability. And for us, we needed end-to-end pipelines where we could stream in all of these things in an efficient and performance infrastructure where these pipelines kind of run automatically left and right. So that's the kind of investments we made to say, hey, this is our infrastructure. But again, we're not a platform company. We're not the Googles or the Microsoft which say, hey, use our platform. What we wanted to do was use these as capabilities that we have internally to deploy differentiated solutions. What we wanted to do was take our differentiated capabilities of predictions and anomalies, which we haven't covered here, and bring that to the customer. So the first industry that we picked was the solar industry. And then we surface that into a use case where we say, this is the product that we do sell. We say, hey, look, as a solar PV manufacturer, as you have different types of data coming from different sources, from your different plant, from your IoT devices, how do you ingest all of that data into a real-time data platform? How do you have so this piece that you saw in the previous slides, how do you have these AI pipelines running? How do you have digital twins of each and every different device to be able to address the use cases being served up by the solar industry? And similarly, we can talk about the things that we do for the solar industry, and our platform for the CRM industry is similar. So for us, being able to take to make some of these investments was justifiable because we were consumers of the same platform, and our ROI multiplies with each new customer coming into the platform. But again, as I said, this may or may not be your typical use case, but I wanted to kind of touch upon that so that the choices of which approach you're taking are clearer. So Ryan, we are definitely 99% of the stuff we do is deep learning. We have found things like XGBoost and CatBoost to be extremely impressive in their simplicity and doing some of the groundwork. We have not found them very flexible to do the core work. So for example, hold on just one second. So for example, we actually use the CatBoost approach to do the introspective quality. And we actually use the XGBoost to do the ensembling. But all of the multi-model, the two-stage model, all of that work, we found it to be a lot more effective through your standard Keras, TensorFlow, deep learning approaches. Any particular topics that we covered? As I said, some of these slides were fairly heavy with a lot of content packed in. I would be more than happy to go back to any slides and shed more light and details. I think as somebody said, the slides would be available after the chat. If you have any questions, feel free to reach out to me. But if there are no questions, we'll probably convene in about a minute's time, giving you a lot of your time back to go back and enjoy yourself. All right. Thank you guys so much for your patience, and appreciate the time. Hopefully some of the things that we shared are going to be meaningful and useful for the stuff that you guys are doing. If not, and as always, please feel free to reach out for any details or any clarifications. Thank you.